Okay, so this is the second video going over the review problems for the Unit 2 quiz on limits and derivatives. So before I go to the problems, like pick up where we left off with the problems from the last video, there are a couple loose ends that I do need to tie up. And the first one is number 1. I realized after making the last video that I only did 1A and I skipped B, C, and D. So let's talk about those real quick. And so first of all, let's talk about part B. It says state the equations of the horizontal asymptotes. All right, so this is B. I'll put it here. And so it looks like there is a horizontal asymptote here as we go in the positive direction, and then another one here as we go in the negative direction. Okay, and so the upper one crosses the y-axis there, and so that one is y equals 4, the one as the graph, as the function is going to positive infinity. Going back to part 4 right here from part A, number 4 from part A. And then the negative, the one going to negative infinity, the other asymptote, looks like it is at y equals -1. Crosses the y-axis right there. Okay, so those are the horizontal asymptotes. And then C says state the equations of the vertical asymptotes. So let's look at that, part C. And so C, vertical asymptotes looks like there is one right here at x equals 0 that the function approaches from both sides. So one of them is x equals 0. And there's another one right over here that that the function approaches from the left. And that is right here at right here at x equals 2. So those are the vertical asymptotes. And now let's look at D. At what numbers is f discontinuous? So f is discontinuous at the following numbers. So right here we have discontinuity. It's a jump, where the function goes from down here at -2 up to 0, and that's at the x value -3. And then there's another discontinuity at x equals 0, because it's going up to infinity in both directions, so 0. And then there's another discontinuity at x equals 2. It's up here, and then on the other end it's going down to infinity. And so there's a jump discontinuity at x equals 2. And then finally at x equals 4, we have a removable discontinuity because the value of the function is down here rather than up there. So if we shifted that point up there, the discontinuity would go away. So that's why it's a removable discontinuity, but it is a discontinuity, so right there at 4. So if we're going to categorize these, this is a jump. This is a removable. Hang on 1 second, let me write that a little bit better. Removable. Okay. 0, that's an infinite. It's an infinite discontinuity, and at 2, it's going to infinite, negative infinity from one side, but we're going to call it a jump because it jumps from negative infinity up to 3. And then, okay, so that's part D. Also, I asked you in the assignment to indicate which what the intervals that the function is continuous on. Now we're going to assume that to the left and to the right of the graph that's shown, there are no further discontinuities, which we don't have any information about it. So if there were discontinuities, we wouldn't have any way of knowing where they were or what type they were. So we'll just assume to the left and to the right there are no more discontinuities. And so the intervals are as follows. All right. So from negative infinity to -3, it is continuous. And we'll say inclusive because it is a filled in point there. And then from -3 non-inclusive up to 0 non-inclusive. And then from 0 non-inclusive to 2 non-inclusive. And then from 2 non-inclusive up to 4 non-inclusive. And finally, from 4 non-inclusive up to infinity, assuming, of course, that there are no discontinuities, other discontinuities beyond what is shown here in the graph. Actually, I realize there's one change I'd like to make because right here at 2, that point is filled in, so we'll actually go ahead and make that a square bracket. We'll make that 2 inclusive. Okay, on the quiz, I'm not too worried about whether you have it as inclusive or non-inclusive at those endpoints, if the circle's filled in or not filled in. But you should be able to identify the intervals on which a function is continuous. All right, so that's going back to number 1. And now the other one that we have to revisit is number 3. And I actually felt a little bit, oops, go away. I don't want you there. Okay. I felt a little bit, how shall I say, silly for not recognizing this. I'm going to go ahead and erase this. But maybe I just wasn't able to think clearly as I was making the video. But afterward, I realized something, which is that the function e to the x, so let me just put a little line right here. And maybe I'll put a different, I should be using different colors here. So note, e to the x is continuous on, I don't have enough space here, but on all the real numbers. Okay, so the function e to the x is continuous on all real numbers. There is no number that I cannot use when raising e to a power. I can raise e to any power. I can raise e to the 0, e to the 5, e to the whatever. And so when I look at this up here, that's just a polynomial, right? So anything coming out of that is a number. And so since I'm only getting numbers out of here, this limit is actually much more easy. I was overthinking it, basically. So what was happening when I was making the first video last night. To find the limit, I just need to plug 1 in for x. And I have e to the 1 cubed minus 1, which is e to the 0, which is equal to 1. So yeah, sorry I didn't figure that out last night, but I guess I was just overthinking it. Okay, so those are the ones I wanted to revisit. Now let's go down to where we left off last time. And I'm going to go ahead and erase some of what I have here. Let me just do it this way. Okay. So we're going to just go ahead and delete that one. Where's my delete button? There we go. That way I've got more space. And so we're going to do number 20. This is number 20. And 20 says, find the limit as x approaches 1 of 1 over x minus 1 plus 1 over x squared minus 3x plus 2. Okay, so if we look at this, we'll notice that both of these expressions, the denominators go to 0. And so it's possible that this limit doesn't exist. But hey, maybe it does. We should try to figure that out. And so the first thing we can do is we can try to figure out how to get a common denominator. And so it turns out that the denominator of the left term is factorable. And so that's going to make it a little bit easier to get a common denominator because I won't have to do as much multiplication. So let me give myself a little space here. Okay, so the denominator on the left factors into x minus 1 times x minus 2. And you can test that for yourself if you don't believe me. And so to get a common denominator, all I need to do is in this first expression, first fraction, multiply the top and bottom by x minus 2. When I do that, I will have a common denominator, and I'll be able to add these two fractions. Oops, once again, I forgot to write limit. So I should have written limit right there. So let's start on the next line. We'll write it. So this is equal to the limit as x goes to 1. And I add these together. And so that's going to be x minus 2 plus 1. And the denominator is x minus 1 times x minus 2. Okay, well, of course I can combine my like terms here. And this gives me, so negative 2 plus 1, I get x minus 1 in the numerator. Oops, I forgot to write my limit again. I keep forgetting that. Okay, so limit as x goes to 1 of x minus 1. And then in the denominator, it's x minus 1 times x minus 2. Okay, well, now I have common factor on the top and the bottom. And keep in mind that, you know, there's a 1 multiplied out there. The x minus 2 doesn't just pop up to the numerator, but I am a lot closer to solving this. So this is equal to the limit as x goes to 1 of 1 over x minus 2. And at this point, I can observe that when I plug 1 in for x, the denominator does not become 0. And so I can go ahead and plug in 1 wherever I see an x. So I get 1 over 1 minus 2. And that is equal to 1 over negative 1, which is negative 1. All right. So that's number 20. Okay. Let's keep going. Those are the limit questions. And the next one I assigned was, I believe, number 29. So let's look at that one. 29 is a piecewise defined function. And it's saying evaluate each limit if it exists, determine where it's continuous, and C, sketch the graph. Okay. When I look at this, I sort of feel like these parts are backwards. I would really like to see the graph first, as that's really going to help me visualize the limits from number 1. So I'm actually going to start with C. And let me think about this. So my lowest value is 0, so I'm going to go, and I have to go past 3. So okay. So here we go. And so 1, 2, 3, 4, 5, 6, 7, 8. That should be far enough. Negative 1, negative 2, negative 3, negative 4, negative 5. I'm not going to label all these, but 1, 2, 3, 4, 5. Okay, so that's positive 5, negative 5. And now let's go ahead and draw these in. It's saying the square root of negative x if x is less than 0. Okay, so square root of x would be a function that looks kind of like this. But this is saying the square root of negative x. And so that will not be defined for positive numbers, right? Square root of negative 1 is not defined. It's not a real number, and we're not working on the complex plane here. We're working with real numbers only. And so it turns out this one is only going to be on the left side, okay? Because if I take a negative of a negative, I get a positive, and I can take the square root of that. For x less than 0, okay, so maybe I should have put sort of a hole in here, but okay. At least as far as the first part of the function is, the 0 is not filled in because it's saying x less than 0, not x less than or equal to 0. Oh, and since it's x less than 0, I don't have to worry about the positive not being defined. Okay, the next one is 3 minus x for x from 0 up to 3. And so let's go ahead. 1, 2, 3. Okay, so this is probably not to scale in terms of this first function, but I'll make it to scale in terms of the second function. So for the second function, the circle is filled in up here, all right? And then it goes down to 3, but we do not include 3, so I'm going to do an open circle there. And this is a linear function going like that. Let me try to do that a little bit better. Okay, good enough. It should be a straight line. I know I didn't do a perfect job of that. And then finally, the next one is for x greater than 3, it's equal to x minus 3 squared. So this is a parabola, but it's, again, it's not greater than or equal to, it's greater than. So it's going to go like this. But we're not filling in that point. So notice that 3 is not in the domain of the function. 0 is in the domain, but there's a jump discontinuity here. This is annoying me. I'm going to try to do a better job. Maybe if I go faster. All right, whatever. Good enough. So now let's go ahead and evaluate these different parts. Okay, so now we're going to A. And the first part is if we're approaching 0 from the positive direction. And let's go ahead and change colors here. I want to make this a little bit thinner too. Okay, so we're approaching 0 from the positive. And if we're approaching 0 from the positive, my limit is going to be 3. Actually, I don't think I have to write it down here. I have enough space over here. So that limit's going to be 3. If I'm approaching 0 from the negative, then it's going to be 0. And the limit as x goes to 0, well, from the negative it's 0, from the positive it's 3. Since those are not equal, the limit does not exist. Okay, and now the limit of 3 from the negative, so we are approaching 0. 3 from the negative, 3 from the positive, we're coming in this parabolic thing, and that's also 0. So that means the limit as x approaches 3 of f of x is 0, because the left side limit and the right side limit are equal. Now, keep in mind that the value of the function at 3 is not defined. However, the limit exists. F of 3 is not defined, but as we approach 3 from either direction, we are getting closer and closer to the value of 0, so the limit is defined, even though the value is not defined. And finally, part B. I'm going to go back to my other color. There we go. So part B, where is f discontinuous? And we see 2 discontinuities. So at x equals 0, we have a jump. and at x equals 3, we have a hole, a removable discontinuity. So those are my two discontinuities. Okay, let's go on to number 33. Number 33 is the next one that I assigned you. And by the way, one other thing about 29, if you're not sure what these functions look like, you can always graph them in your calculator. I've got my calculator thing here, and I haven't been using it. But for example, if you didn't realize what the square root of negative x, what that function looked like, you can just put in your calculator, and let's see, it's square root of negative x, and hit OK. And now we graph it, and boom, there you go. You see it has that shape that I drew there. So you can always graph these as a way to, yeah, and you can always, plug in the points into the function and make a table, all those things. But the more you work with these functions, the more you get to know what they're going to look like. Okay, so let's go on to 33. And ooh, yeah, 20 minutes already. Wow, I gotta talk faster. Okay, so 33, we're probably going to want to use the intermediate value theorem. And in fact, I didn't copy the instructions over here. It might even say use the intermediate value theorem. But the question is there a root between 1 and 2? So in the text it says, is there a root between those two x values? And so first thing we're going to want to do is plug in those two x values. So we have 1 to the 5th minus 1 to the 3rd plus 3 times 1 is 3 minus 5. And let's see, this is 1, that's 1, those cancel out. 3 minus 5, this is negative 2. And now let's plug in 2 and see what y value we get at the x value of 2. Okay, so 2 to the 5th power minus 2 to the 3rd power plus 3 times 2 is 6 minus 5. Okay, so 2 to the 5th is 32. 2 to the 3rd is 8 plus 6 minus 5. Okay, so 32 minus 8 is 24, plus 6 is 30, minus 5 is 25. Hopefully I got that right. Either way, even if I was off slightly, it's quite clear that this is going to be positive. And so what this means, if we think about the potential graph of this function, at 1, it's negative 2. And at 2, it's, it's up here somewhere. And we don't necessarily know how many places it crosses the x-axis in this interval. Who knows? Maybe it goes up and down. Now it's a degree 5, so I don't think it could go up and down that many times. Or it might just, go one time. But the point is, if it's going to go from the negative to the positive, it has to go through the x-axis, which means there is a root between 1 and 2. There has to be a root. Because it's a polynomial, it is continuous. All polynomial functions are continuous everywhere. And you know what? Let's go ahead and graph it. Since we are on the problem, let's go back to expressions. Okay, I'm going to clear this one out. Add an element. All right, and x raised to the 5th power minus x raised to the 3rd power and plus 3x minus 5. Okay, so that is my function, and I can graph it. Ooh, so kind of it made my y-axis really big, and so I can't really see where the root is. So I'm going to change the y-axis here. And so axes, values, wait, let's see, no. Now I don't remember how to use my calculator. Navigate? Probably not. Zoom, plus or minus. but I don't want to change it that way. Alright, how do I do this? Auto, we'll do that. Well, I guess I could trace it, couldn't I? But I want to actually see it on the thing. What happens if I go to navigate? No, that'll just allow me to do that. Display values. No, that's not what I'm looking for. How do I change my window settings? If I was using my TI calculator, I would know it. Make axes equal. Maybe it is in here. Oh, you know what? I bet it. You know what? There it is. I just had to go in there. Okay, so I don't want auto. I want, let's see, -5 up to, I guess we can go up to like 30. So I get the 25 in there. Okay, and let's confirm that. And, oops, no, don't want to do that. Confirm. Okay, so now I look at my function and I see that sure enough it crosses the x-axis right there between 1 and 2. Looks like, I don't know, around 1.5 maybe, or 1.4, something like that. So there we can see it on the graph. Okay, let's keep going because we got a good bit more to go. Oops, hang on, I gotta, oh, 35 is here. Okay, we're gonna do 35 and then I realized I didn't copy in the rest of the problem, so I'll have to pause the video or make another video, but we can go ahead and do 35. Okay, so 35 is getting into the realm of derivatives. Okay, so it says find the slope of the tangent line to the curve at the curve y equals 9 minus 2x squared at the point 2, 1. And so we can go ahead and accept that 2, 1 is in fact on that curve. And we want to find the slope of the tangent line when x is equal to 2. So let's go ahead and use the definition of the derivative. So the limit as h goes to 0 of f of x plus h minus f of x divided by h. And I'm just going to go ahead and plug in 2 for my x value. And so this gives me 9 minus 2 times 2 plus h squared minus f of 2, and we know from the problem description, the fact that 2, 1 is one of the points. If I input 2, the output would be 1, and you could always test that as well. So f of 2 is 1. All right, and then this is all divided by h. Ah, yes, once again, I forgot to put the limit there. Okay, so it should say limit right there. So the limit as h goes to 0 of the following expression. We have 9, and we'll go ahead and FOIL out this part right here. So minus 2 times 4 plus, let's see, it'll be 4h plus h squared minus 1. And this is all divided by h. And that is equal to the limit. Let's see what simplifications I can do. As h goes to 0, And so this distributes, and I have 9 minus 8 plus, nope, minus, because I'm multiplying by -2, minus 8h minus h squared minus 1, all divided by h. Okay, so I have a -8 and a -1. Those will combine to give me a -9, which means all of that cancels out. And then I can also factor an h. In fact, let's factor -h out. And so I'm going to have the limit as h goes to 0 of -h, and what's left inside there is going to be 8 plus h divided by h. Okay, so cancel out, and go on to the next line. This is the limit as h goes to 0 of -8 minus h. Okay, well, since h is going to 0, then this is just going to equal -8. So that is the answer to part A. The slope of the tangent line to the curve is going to be -8. Okay. Now, the second part, part B, is asking for the equation of this tangent line. Okay, so all this right here, this is all part A. Okay, so now we're going to do part B. And part B, I can just use the point slope form. Y minus y1 equals m times x minus x1. Well, I know the slope is -8, so I put that in for m. And then I know that I have the x value 2 and the y value 1. And so I'm going to have y minus 1 equals -8 times x minus 2. So that is the equation of the tangent line at the point 2, 1. All right, number 35, complete. All right, let's go on to number 37. Oops, what's going on here? 37, okay. So we just finished number 35 and 37. So the displacement in meters of an object moving in a straight line is given by, given by that equation right there, where t is measured in seconds. So part A, we want to find all these average velocities over the time period. And so what we are going to need to do is use our slope formula. So slope formula says m is the change in y divided by the change in x, and that is y2 minus y1 over x2 minus x1. So for the interval 1, 3, first of all, we know that the slope, the change in x, is going to be 3 minus 1. Okay, and then let's plug 3 into the equation up here, and 2 times 3 is 6. I should actually just write it out so I don't make a mental math error. Okay, 1 plus 6. Hang on, let me put the brackets here. 1 plus 6 plus 9/4, because 3 squared is 9. Okay, so plus 9/4 minus 1 plus 2 plus 1/4. Okay. And now I just have to do a bit of fractional arithmetic here. Well, 9/4 is going to be, what, 2 1/4? And so 1 plus 6, 7 plus 2 1/4 is going to be 9.25. And then 1 plus 2 is 3. Plus 1/4 is 3.25. And divide that by 3 minus 1. And so what am I going to get there? On the top I'll have 6, on the bottom I'll have 2, and so this slope is going to be 3. That's for part 1. Alright, for part 2, the interval from 1 to 2. And so for this interval, I'm going to plug in, so I know on the bottom I have 2 minus 1, and on the top I know that I'm subtracting 3.25, but let's plug 2 in, and let's just use my calculator here. I'm going to make my life a little bit easier on myself here, and go back to the main. Okay, so plug this in the calculator. So 1 plus 2 times 2 plus 0.25 times 2 squared, which is 4, and that's going to be 6. So I have 6 minus 3.25, and that's going to be 2.75 over 1, which is equal to 2.75. All right, now let's do the next one, the interval 1, 1.5. Okay, so I'll draw these things here so we know we're working on separate problems, or separate parts of the problem, I guess. And so in the denominator, I have 1.5 minus 1, and in the numerator, let's go ahead and pop it over here. So 1 plus 2 times 1.5 plus 0.25 times 1.5 squared, and that is equal to 4.625. Okay, so 4.625, or sorry, 4.565. Let's fix that. Come on, you know you want to. All right, 4.565 minus 3.25. Okay, so let's go ahead and do it here. Oh, oops, we're going to do answer minus 3.25, and then divide that by 1.5 minus 1, which is 0.5, and I get 2.625. Okay, so 2.625. And at this point, we can start guessing, if you want, like what slope we're sort of homing in on. And let's go ahead and do the next one. So this is that was part 3, and now we're going to do part 4. And so that's find the average velocity on the interval 1, 1.1. Okay, so in the denominator, I have 1.1 minus 1, and in the numerator, let's plug it in. So 1 plus 2 times 1.1 plus 0.25 times 1.1 squared, and that's going to equal 3.5025. 3.5025 minus 3.25. Okay, so answer minus 3.25, and I get 0.2525, and I'll divide that by, well, in the numerator, 1.1 minus 1 is 0.1, so I divide by 0.1, and I get 2.525. Now, what slope do we think we're approaching? When I see it go from 3 to 2.75 to 2.625 to 2.525, I'm going to imagine that maybe it's going to 2.5, but maybe not. You know, that would be a nice sort of round number. But who knows? It might be approaching something totally different. But we're going to find out in part B. Part B, we're going to figure out exactly what the instantaneous velocity is. And let's see, I'm going to go ahead and erase these parts up here, and I'm going to do it right up here. All right. Go away, go away. Come again another day. I'll erase this part too. Thanks for waiting, all my viewers. Or, you know, speed up through this part, obviously. You don't need to watch me erase. Okay, where are we at? We're going to use the limit formula that... Hello? Where are you, cursor? My cursor is disappearing. Okay, the f... Hang on. Let me move this down a little bit. Maybe that'll work better. Okay. That f prime at 1 is equal to f of 1 plus h minus f of 1 divided by h. Okay, I already know no, come on, go away. All right, my pen is not working out too well right now. I already know that f of 1 is equal to 3.25 from the earlier part. So let's put that up there. Remember that. And let's do the other part. So let's see. I have 1 plus 2 times 1 plus h plus 1/4 times 1 plus h squared minus 3.25. All of that is divided by h. And dang it, I forgot to put my limits in again. The limit as h goes to 0 of this expression. So I want to find this limit. The limit as h goes to 0. And that should have been written right there too. Okay, so let's see. I'm going to have to square this out. And so I'm going to have 1 plus 2 plus 2h. I get that when I distribute here. And then I'm going to have, this is 1 squared is 1. I'm going to go ahead and multiply by the 4th, so I don't have to write out another step. And then 2h, so that's going to become h over 2 when I multiply by a 4th. And then h squared, so that's going to be h squared over 4 when I multiply by a 4th. And this is all subtracting 3.25. Okay, and then that's all over h. And this, once again, is the limit as h goes to 0 of all that. Yeah, we're looking kind of intimidating here, but with some persistence, we can get there. It's going to take some persistence, but we can definitely get there. I'm just going to erase the rest of this so I have as much space as I need. There we go. Okay, so first of all, notice that 1 plus 2 plus a 4th is 3.25. So positive 1 plus 2 plus a 4th is 3.25, and that's a negative 3.25. So that all cancels out. Then I have 2h plus h over 2. So that's, what, 2.5h, I guess. So, well, let's see. Maybe, you know what I'll do? I'll multiply top and bottom by 4, and that way I'll get rid of all my fractions. And then I can go from there. Who loves getting rid of fractions? So multiply top and bottom by 4. And so on the bottom, I'm going to have 4h. And then on the top, I'm going to have 8h plus 2h plus h squared. Okay, so that's the limit as h goes to 0 of 10h plus h squared, all divided by 4h. And now, when I factor the h out of this, we're going to see that this is the limit as h goes to 0 of h times 10 plus h. And then on the bottom we have 4 times h. These h's cancel out. And now I can plug 0 in for h. And I get 10 over 4, which is equal to 2.5. Which, if you recall, the numbers that I was approaching on these intervals, yeah, they looked like they were getting closer and closer to 2.5, and it turns out 2.5 is, in fact, the instantaneous velocity. Cool, so good news. That's number 37. Number 41. How are we doing here? Are we going to hit an hour? We're 46 minutes, 47 minutes in the video. We might hit an hour on this video, folks, but hey, it's worth it. Time flies when you're doing calculus, right? All right, the total cost of repaying a student loan at the interest rate of R% per year is given by some formula. What is the meaning of the derivative f prime of r, and what are its units? Okay, so let me just go ahead and, draw this line here. We indicate we're on a different problem. This is 41. Okay, so the cost we're paying is the total cost, right? Let's keep this in mind. This is not the cost per month. This is total cost. Is dependent on the rate. It's a function of the rate. The higher the rate, the more the cost. The lower the rate, the lower the cost, presumably, right? And so f prime of r is the change in the cost, right? Derivative means change. And so basically what it's saying is, as we change r, how is the total cost changing? Presumably, if you increase r, it's going to, it'd be a weird function that this student loan company was using if this wasn't the case. But almost certainly it's a standard exponential function that is being accumulated over time. And so if r goes up, then the cost increases. If r goes down, the cost decreases. So f prime of r is the change in rate. And so what are its units? Well, I would say, it's probably dollars per percent point, something like that. So if I increase a certain amount of percent points, because the units of cost is going to be dollars, right? And so I would say it's probably going to be dollars per percent of some kind. And I mean, you could do whole percents or fractions of percents, but probably you just do whole percents. Okay, what does the statement, so that's part A. Part B is, what is the statement f prime of 10 equals 1200? What does that mean? Well, it doesn't mean that if the rate is 10%, that the total cost is 1200. What it means is that when you are at, and maybe it's easier to explain this with a graph. So let's think of this as, let's call this C, okay? And so we'll call this 10 right here. So what it means is that at this x value, I have a certain cost, but the instantaneous rate of change is going to be 1200. So when we're at 10%, the slope of that tangent line is 10, meaning that going from, say, 10% up to 11% is going to increase the total cost of the loan by, it's not exactly 1200 because then we'd be doing a secant line, an average rate of change, but it's going to be, probably a little more than 1200, increasing it from 10% to 11%. And also, if we were increasing it from 9% to 10%, it'd be a little less than 1200. But yeah, 1200 is the amount that the total cost is changing by when you hit that rate of 10%. Okay, is f of r always positive, or does it change sign? Okay, so let's go ahead and assume that this is a standard kind of function that a bank or a student loan company is going to use, and that's an exponential function. And so so what that means is that whenever the rate changes, whenever the rate increases, the cost increases, and whenever the rate decreases, the cost decreases. So f of r, or f prime of r, is always positive. Positive. The cost function is an increasing function, and therefore the derivative of the cost function is always positive. All right, so that is 41. Let's talk about 43 and 44, I believe, are the ones that I assigned you. So 43 right here. And I'm going to go ahead and draw the derivative right over top. You can also draw a separate axis and trace this one, draw the derivative below, but I'll go ahead and draw the derivative right on top. So I see right here, I have a zero slope there, a zero slope there, and a zero slope there, which means that the derivative, the value of the derivative is the slope of the original function. So a zero slope means a zero value here. A zero slope means a zero value here. And a zero slope means a zero value here. Okay, so now on this interval, right here, the function is decreasing. It's going down. The slopes of the tangent lines are negative. So decreasing function, negative slopes mean negative values. And right here, the function is increasing. So let me draw it a little bit better here. So negative slopes, negative values, positive slopes, positive values, okay? And then as we go further to the right, we see that the function's going down, and so the slopes are going to be negative, and so the derivative is negative. It's below the x-axis. And up here, the values of the function are increasing. Derivative is positive, and so it's going up. So the derivative looks something like that. I didn't do a perfect job of this, did I? So let me draw that a little bit better. Yeah, so something like that. That is the graph of the derivative. All right, let's do number 4. And we see, and again, I always start by finding the points where the slope is 0. And so here we go. That means that the value of the derivative is going to be 0 here because the slope is 0. And right around here, we have another 0 slope, so value of the derivative is 0. Here we have something interesting going on. We have a corner, which means there will be a discontinuity in the derivative. The derivative is not defined at a point where you have a sharp corner. So let's deal with that last. And let's first deal with this part right here. Here we see the function is increasing. And so we'll go ahead and draw positive values of the derivative. Okay. Oh, I missed a point, didn't I? Okay, here is another point where the derivative is 0. Okay, so in this little interval, it's decreasing, so I'm gonna go ahead and put that in there. Oops, let me try to do a better job of that. Okay, there we go. Not perfect, but all right, I'm gonna try to do a little better job of this. Okay, there we go. And now we see it continues to increase in this interval until we get to that x value. So, okay, so let's go ahead and make it continue to increase. And here we have a hole. And we see it then sharply turns negative, and it looks like a straight line. And so at this x value, let me go ahead down here. I'm not too worried about the exact y value, so I'll just go ahead and put a starting point there, and it's going to be flat. So some y value, I don't care exactly the y value. Oh, and finally we got one more section here. We see in this section the values are decreasing, right? The function is decreasing. The slopes of the tangent lines in this area are negative, and so the derivative values are negative. And I can put an arrow there, so it's kind of, oops, it's increasing in the negative direction. So that is what the graph of the derivative of 44 would look like. All right, we hanging in there? Let's finish this up. Let's stay strong. Let's persevere. Let's go all the way through. Number 45. Ooh, okay. This is a fun one. I can tell already. I can feel it. Okay. Letter A, part A, says use the definition of the derivative to find f of x. So we're not finding the derivative at a single point. We're finding the derivative of the whole function. And I'm going to use my difference quotient that the derivative f prime of x is equal to the limit, yay, I remembered to write that this time, the limit as h goes to 0 of f of x plus h minus f of x, all divided by h. And so let's go ahead and put this in here. This is going to be the square root of 3 minus 5 times x plus h, and minus the square root of 3 minus 5x, all divided by, oh, wouldn't you know it, I forgot to write the limit, didn't I? Alright, there we go. Should say limit in front there. And now, in order to make any progress here, the tool that comes to mind is multiplying by the conjugate, top and bottom. So let's multiply top and bottom by the square root of 3 minus 5 x plus h minus, or plus the square root, because it's the conjugate, 3 minus 5x. This kind of looks like 5 times x. Let me make that minus sign a little longer. Okay, multiply by the bottom by the same thing. 3 minus 5 times x plus h plus square root of 3 minus 5x. Okay. And let's come down to the next line. This is equal to the limit as h goes to 0 of, and let's hope this conjugate thing works because it's a bit of work, right? Okay, so I have the squares of these two parts, and I have the square of those two parts, and the inner and the outer cancel out, which is why we do the conjugate. So in the numerator, I'm going to have 3 minus 5 times x plus h minus 3 minus 5x. And on the bottom, I'm going to have the h times the square root of 3 minus 5 times x plus h plus the square root of 3 minus 5x. Okay. All right, let's see what simplifications I can make here. Well, I see I have a And I realized I made a mistake. I should put that in parentheses. Okay. So I have the negative 3 cancels out with a positive 3. I have a negative of a negative 5x. So this distributes and I get a positive 5x. And when I distribute this, I'm going to get a negative 5x. So that cancels out. But I also have to distribute the negative 5 to the h. Okay. And so what am I going to get here? I'm going to get that this is the limit of h goes to 0. And let me make sure I'm doing this right here in terms of negatives and such. Yeah, that all cancels out, and I have it's going to be negative 5h. Okay, so in the numerator, I have negative 5h. Come on. I'm trying to get this to erase. It's not erasing. I want to write a little better. Okay, negative 5h. And in the denominator, I have h times the square root of 3, okay, all this stuff, right? And then the h cancels out with this h. Once those h's cancel out, I have the following limit. Limit as h goes to 0 of negative 5 divided by the square root of 3 minus 5 times x plus h plus the square root of 3 minus 5x. Okay, there's only one h left, and so I can easily just go ahead and take this h as it goes to 0, right? That's going to go away. That goes to 0. And so when I plug that 0 in, my final answer is going to be that this is negative 5 divided by 2 times the square root of 3 minus 5x. Okay, that is my limit. Whew, that was a bit of work. Find the domains of f and f prime. Okay, so the domain of the square root is anything that's positive. So the question, let me see where let's erase this here, and I'm going to write this right down here. Okay, so this is part B. So the domain is wherever 3 minus 5x is greater than 0. Okay, and so it's a simple little inequality to solve. I subtract 3 from both sides, and I have negative 5x is greater than negative 3. And I divide both sides by negative 5, which means I flip the sign when I do that. I'm going to get x is less than 3 over 5. Alright, this is a bit annoying. It's trying to erase this thing. I want to write a better 3 and it won't erase. Come on. Come on. Okay, there we go. Finally erased. 3 over 5. Okay, so that's the domain. And it's actually the domain for both functions. The derivative, the original function, and the derivative. Because, well, not quite, I guess. Because in the original function, it could be greater than or equal to. Because I can take the square root of a negative number. Or sorry, I can take the square root of 0. Can't take the square root of a negative number unless I'm working with complex numbers. But I can take the square root of 0. However, if you notice here, when I take the square root of 0, I get a 0 in the denominator. That doesn't work out. So this is the domain for f of x. For f prime of x, the domain should be x is less than 3 over 5. Okay, so that's for f prime of x, because that way I avoid having the 0 in the denominator. And part C says go ahead and graph these functions. Let's go ahead and do that. So let's go to my grapher, and the expression says we're going to graph them both on the same screen, and we'll see if our answer seems reasonable. So first I'll graph f of x. So the square root of 3 minus 5x. Okay, put that in. And we'll add another one. Oops. And the other one is, let's see, negative 5 divided by 2 times the square root of 3 minus 5x. Enter. Okay, I think that's what we got. And so let's go ahead and graph these two functions. Let's go ahead and do the auto. And there we have it. And so, does this seem reasonable? Well, we notice that the green function, which is the original f of x, is the green, is a decreasing function. The slopes are always negative. And then the yellow function, which is the derivative, has values that are always negative. And so, yeah, that seems reasonable to me. You see it shoots down as x gets closer and closer to 3/5, which means that's where the derivative is going to approach 0. As the x value approaches 0, the derivative goes toward negative infinity, which also validates these domains that we got. So yeah, I feel like this graph validates the work that we did. Okay, we're really close. I can smell it. Hour and 6 minutes in. We're almost there. 48, second to last one. The figure shows the graphs of f, f prime, and f double prime. Identify each curve and explain your choices. Okay, so first thing I do is I look at this and I say, okay, there's a 0 slope here and a 0 slope here, and the green one is 0. So the green one must be the derivative of one of those two, but it can't be the derivative for both because these are two different functions. So then we think about this a little more and we say, okay, I see right here and right here, I also have 0 slopes. And so the green function does not have the does not have zeros at those two. Okay, so what does that mean? That means that the green function must be the derivative of the red function. So let's think through this. Would it make sense to say A is f? If A were f, then C would be f prime. Okay, and let's think about whether that makes sense, because that would mean that B would be f double prime. And if we look at C, we see that it does have these two spots where the derivative should be 0, and sure enough, my function crosses there, right here as well. Okay, and so those are the only two zeros of the blue function. They match up with the places where the green function has a 0 slope. The tangent line would be 0. And so that looks good to me. So we're going to say f is A, f prime is C, and f double prime is B. Okay, last one, folks. We are almost there. Let P of t be the percentage of Americans under the age of 18 at time t. The table gives the values of the function in census years from 1950 to 2010. What is the meaning of P prime of t? Okay, since P of t is the percentage of Americans under age 18, so P prime is the change it's the change. I'll write it this way. So the change in percentage, and it's percentage of time, and so time is in years. So percent per year is really what it is. It's the change in percent of Americans under the age of 18 in percent per year. So the units are percent per year. Construct a table of estimated values for P of T. So here I would just take the differences, and maybe I'll go ahead and use the midpoints. So I'll go ahead and so P prime of T, and I'll use the midpoints because that makes the most sense to me. So 1955, and the difference is let's see, 4.6 from 31.1 to 35.7. So that percentage difference is about 4.6. And then 1965 is a negative 1.7. 1975. We've gone down a lot there. So Americans are getting older in the 1970s. We're going down by 6%, negative 6%. All right, and then 1985, we've gone from 28 to 25.7. So that would be 2.3, negative 2.3. Oops, I wrote the wrong thing. And it won't erase. Come on. Come on. Come on. Let's see if I can do it this way. Come on. Erase. Come on. Oh, that's really not what I want. Let's delete the whole thing. Okay, let's try this again. Negative 2.3. All right, 1995. And so that's the difference here. That is 0. That didn't change at all. And finally, 2005. So 2000 to 2010, the change was negative 1.7. So what we're noticing here is, in general, that the trends is that fewer Americans are under the age of 18. The most dramatic change coming in the 1970s, when we had a drop of 6%. Okay, graph P and P prime. How would it be possible to get more accurate values of P prime? Yeah, you know, what I would do is I would do a polynomial model probably, and this is not something you would have to do on the test. On the test, you should at least have the basic understanding of how to find change from a table and the general trends. However, if I did want to do this, I would probably make a polynomial model of the original function and then find the derivative of that polynomial model. And or actually another way would be to look up more data, and I guess probably we wouldn't have, I don't know if that really exists, because the census is, the official censuses are taken every 10 years. I'm not sure if we'd have accurate intermediate data. But if it were possible to get data every 5 years or every 2 years or every 1 year, then those, you know, would improve our accuracy, I guess, because we know the change per year. So I'm going to leave it there. I think we've done enough. And yeah, good luck.